Optimizers, project is the optimization of DLP CMOS technology. The goal of our project is to test and model effects of light on transistors and memory array parasitics in order to better represent DMD performance. Unlike most ICs, the DMD is not opaque, therefore light in the package will actually have an effect on the transistors inside. In order to test the devices, we needed a method of contacting the probe pads on the wafer. To do this, we actually had a probe station and then used probe manipulators to land the probe tips on the contact pads. The sealed environment of the probe station allows us to tightly control the light that hit the wafer and shine light on the wafer. We use an LED light engine provided by TI in order to shine light actually into the probe station. Results of our light testing have shown that the non-isolated NMOS devices experience a large increase in off current when exposed to the light, especially red light. The PMOS devices and isolated NMOS devices are much less affected by the light. And this is due to the wells present in both the PMOS and isolated NMOS devices, which prevent the electron hole pairs formed in the bulk by the light from reaching the channel and adding to the carriers that are already there. The next step was to modify the Spice transistor models to adjust those for the effects that we had found. Unfortunately, due to the model limitations, we were unable to adjust the electron hole pair generation rate. So instead, we found a substitute and used the interface trap capacitance. For the memory rate testing side of the project, we performed both static and dynamic tests. For the static testing portion, we used a probe station, an LCR meter, and a semiconductor characterization system to find the resistance and capacitance for the word line, bit line, and BSA levels. To make that testing a little bit easier, we modified a program that was already on the semiconductor characterization system to run sequential tests. And then to ensure that we got the most accurate results, we actually ran an open correction before each test to remove any stray resistance or capacitance. And then for the dynamic testing, we used a probe station again with a signal generator, oscilloscope, and the active probe to find the rise time, fall time, and propagation delay. We then took all that information and used it to modify the resistance and capacitance of the memory schematics, and then ran simulations using those new schematics to ensure that those results actually match our test data. Thank you for your time. I'm happy to answer any questions you may have.
It's a good comment. You presented really well. I understand what you said, but I felt like you were burning the coal in my eye. Spread that burden around.
So what's TI going to do with this information?
What they can actually do with this is use it to solve the off-current problem the light's caused. They had actually had an idea about what happened, but had never actually done the testing themselves to actually get, quantify, okay, it increases by this much. And so that's what we were able to provide to them. We've also provided they can now simulate, because we've adjusted the models to show these effects. And as I said before, with the wells, being able to isolate the devices in order to prevent in large part this increase in off current, we've also provided a solution.
Well, that would be changing their actually CMOS technology. Since it's a light problem, I realize that the mirror's tip and some light is inevitably going to reach the surface, but would any possible filtering or building in some shields to prevent excess light getting in, is that a possible solution? You look at that.
It is actually another possible solution, since the generation rate with regard to depth decreases rapidly once you actually add several more microns and say passivation layer. Something like that would also be an additional solution.
Did you test it on different devices or wafers, or just one?
Yes, we did on both, we did several different transistor types, both NMOS and PMOS. It wasn't just one type, it was several different types. So we got a
Several different of the same type, just to see if there were any differences.
Yeah, I mean, we got a good sort of range of transistors that we were able to test.
Did you tell us who did what? I probably
Oh, no. Me and Ian were responsible for the light testing. In addition, I did the modification to the transistor models. Sydney, Harrison, and JP were all responsible for the memory testing.
Right, so back to 5 minutes.